Alright, so today I'm going to discuss the forces of lift and drag. Now, these are aerodynamic forces that an object in a fluid, be it a liquid or a gas, will experience. However, they are used most commonly in relation to airplanes, so I'll use those for my examples. I'm going to start with lift. Now, lift is the force that counteracts the mass of the airplane times the acceleration due to gravity, more commonly known as the airplane's weight. Now, for the plane to take off, the lift needs to be equal to the weight of the airplane times the cosine of theta. And I'll show you why this is. So, this here is going to be our airplane. It's a nice big tail there. And this line I'm drawing now is the horizontal line. It is perpendicular to the ground. Now, weight, as you might expect, goes directly downwards. That is the direction of the force of weight. And the lift is perpendicular to the direction of movement. However, planes do not move in a horizontal direction. They actually move slightly above the horizontal. And in doing that, they create an angle theta with the horizontal. And as I mentioned, lift is perpendicular to the direction of movement. Now, we can actually split this weight force into components. And in doing that, we form a right triangle with an angle of theta here. Now, we can figure out the length of this side of the triangle using trigonometry. And that is the cosine of theta times the weight, or mass times gravity, because they're the same, of the airplane. Now, as you're going to see, lift only needs to counteract this component of the weight, because it can only counteract what it is parallel, or anti-parallel in this case, to. This other component of the weight, which is the sine of theta times mass times gravity, is counteracted by the thrust. Now, if we take the cross-section of a wing, we find what is known as an airfoil, and this is what generates lift. Of course, this brings up the question, how does an airfoil generate lift? Well, there are a couple different ideas for this. The first of these, that I'm going to look at, involves Bernoulli's principle. Now, Bernoulli's principle states that if a fluid's kinetic energy increases, then that fluid's pressure must decrease. Now, this can be explained through conservation of energy. Let's say we have a section of fluid with a given amount of total energy, E. Now, for the most part, this energy is constant. It cannot increase or decrease. Again, for the most part. Now, for the purpose of this example, let's say that that fluid's total energy is equal to its kinetic energy plus its pressure. Now, this is because pressure can be thought of as a sort of energy. Now, if we increase the kinetic energy of the fluid, i.e. it moves around really fast, then its pressure must decrease in order to keep the total amount of energy the same. Now, before I relate this to the airfoil, I need to introduce another principle. This one is based on the conservation of mass. It states that a fluid travels through equal amounts of volume in equal amounts of time. So to explain this, I'm going to have this pipe here. Now, for this pipe, it has a cross-sectional area here of, we'll call it A. And fluid moves through it at a velocity v. Now, we can multiply A times v to figure out the volume of fluid that travels through a given point in a certain amount of time. Now, this, as the principle states, must be constant throughout the entire tube. Which means that over here, when we have a much smaller cross-sectional area, we need to have a much larger velocity. It's the same idea behind when you attach a nozzle to a hose. The water shoots out at a much higher velocity. Now, lastly, air can be approximated to move through the sky in what are essentially air tubes. Now, it doesn't actually move through the sky in air tubes, like you can't actually go to the sky and measure air tubes, but it can be approximated to do such. So here we have this air tubes that the airfoil is moving through. Now, as you can see, for the air tube that goes above the airfoil, the cross-sectional area here is much smaller than the cross-sectional area here, Well, it's just the opposite for the air tube that goes beneath the airfoil. The cross-sectional area here is much larger than the cross-sectional area before reaching the airfoil. Now, what this means, according to this principle, is that the air must move at a much higher velocity above the wing than below the wing, because it speeds up here, slows down here. Now, then according to Bernoulli's principle, the air pressure is low here while increased here. Now, whenever there is low pressure, air in high pressure always wants to go to it. Like, high pressure air always wants to go to low pressure air. This creates a force that pushes up on the wing, which we know as lift. Now, the other accepted way as to how lift is generated involves Newton's third law. Now, Newton's third law states that for every action, there is an equal and opposite reaction. So this applies to airfoils by stating that as they fly through the air, they redirect the air downwards. Now, redirecting this air downwards requires a force, which means that there is an equal and opposite force pushing upwards on the wing. And this is where lift comes from. Now, I would like to point out that while these are called Newton's and Bernoulli's ideas, they were not developed by Newton or Bernoulli, but rather other people came up with these theories using Newton's or Bernoulli's principles. Furthermore, there is no consensus onto which one of these is correct. They both have their merits, and it's possible that they could be both correct, but there isn't one that's officially defined as to be the right way. Now that you have an idea as to where lift comes from, you might be wondering as to how we calculate lift. Well, luckily there's an equation for that, and it states that lift is equal to 1/2 times rho sub air times v squared times s times c sub L. And I'll get to what each of these variables are in a little bit. But before I do that, I'm going to address another question you might be having, which is, well, wait, can't we use that equation you introduced at the beginning, which stated that the lift is equal to the mass of the airplane times the acceleration due to gravity times the cosine of theta? Can't we use that to calculate the lift? And you can, but only when the airplane is in equilibrium, i.e. all the forces on it are balanced. However, the airplane isn't always in equilibrium. For example, when the airplane takes off or lands, it's not in equilibrium. This equation was only to show the minimum value lift had to be in order for the airplane to take off. I really should have written it as the lift has to be greater than or equal to the weight of the airplane times the cosine of theta for it to take off again. So, while yes, you can use it when the airplane is cruising, but the airplane won't always be cruising. Much more reliably, you can use this bottom equation. And so now we'll go through the variables for it. Now this L here is lift, which I've been discussing about this entire video so far, so you should know what it is. And it is measured in newtons, because it is a force. And this 1/2, they're just numbers. This P-looking thing here is the Greek letter rho, which is the variable used for density. And the subscript air indicates that specifically the air density. So this variable is the air density, which is measured in kilograms per meter cubed. This V, then, is the velocity of the airplane, which is measured in meters per second, and of course, squared. This S is then the surface area of the wing, which is measured in meters squared. This C sub L, then, is the coefficient of lift. Now, to actually calculate the lift, you need a lot more variables than what I have listed here. And the coefficient of lift essentially combines all of those variables into one term to make the calculations easier. Now, because of that, you do need to determine coefficient of lift experimentally, whereas these others can be measured outright. And furthermore, because coefficient of lift is a coefficient, it is unitless. But that is how you would calculate lift. I'm going to switch to drag. Now, drag is the force that opposes airplane movement. In many ways, it is equivalent to friction. Now, when the airplane is in equilibrium, drag is equal to the thrust minus the mass of the airplane times the acceleration due to gravity times the sine of theta. Now, you may notice that this is the parallel to the first lift equation I mentioned. And I will go through and show you how I arrived at that. So, for that, I'm going to need our airplane and our dotted horizontal line that is parallel to the ground. Now, weight is still going directly downwards, and thrust is still slightly above the horizontal, which creates an angle of theta with the horizontal. Now, drag, as I mentioned, opposes the direction of movement, so it is in the opposite direction. Now, like before, we can split our weight into that right triangle, with the angle of theta being there. Now this time, we want to find the length of this side, because this is the side that interacts with drag. And the length of that is mass times gravity times the sine of theta. Now, as we can see, drag is essentially equivalent to thrust. However, the weight of the airplane does take away some of the thrust, so we need to subtract it from the thrust, and that is how we get drag. Now again, this is when the airplane is in equilibrium. However, for example, when the airplane is taking off, the thrust will have to be greater than the drag. So in reality, the drag is less than or equal to the thrust minus the weight of the airplane times the sine of theta. Drag can be split into two main parts: profile drag and induced drag. I'm going to start with profile drag. Now, profile drag can be further split into two more parts. The first of these is air friction. So earlier, when I said that drag can be essentially thought of as a form of friction, that is, at least in part, entirely true. Now, air friction arises from when the airplane moves through the air and encounters all these different air molecules which bounce off of it. So, for example, think of when you're wading through some water and it takes a lot of force to move your legs. Well, the same thing happens when you're moving through the air. It's just that since air is so much less dense, you don't really notice it. Well, that same situation can be applied to the airplane. The airplane essentially has to wade through the air, and all of the air molecules bouncing off of it create a form of drag. Now, the other part of profile drag comes from a pressure difference. So as the airplane is moving through the air and pushing it out of its way, it creates a low-pressure gap behind it where there are very few particles. Now, as I mentioned earlier, whenever there is low pressure, areas of high pressure always want to go to it. So this causes the surrounding air to circle in behind it, creating what is known as a wake. And this is the exact same thing that is created behind a boat when it moves through the water. Now, this low pressure system also pulls back on the airplane, which creates the other form of profile drag. So, you remember earlier when I was discussing how lift was generated, and I said it was either from a low pressure, high pressure difference across the wings, or from the wings redirecting the flow of air? Well, both of those affect the direction that air moves. And whenever that happens, drag is created. So, however lift is generated, when the air that was used to create the lift rejoins the surrounding air, vortices are created behind the wings. And these vortices is what creates induced drag. Now, since lift creates induced drag increases as lift increases. Now, there is actually an equation to calculate drag. And it states that drag is equal to 1/2 times rho sub air times v squared times s times c sub d. Now, you may notice a few similarities between this and the lift equation, and many of the variables do overlap. Now, this d here is the drag, which I've been discussing throughout this entire second half of the video, so you should know what that is. And because it is a force, it is measured in newtons. This 1/2 is still just numbers. This rho sub air is still the air density, which is still measured in kilograms per meter cubed. This v is the velocity of the aircraft, which is measured in meters per second. Now, because the variable is squared, I'll go ahead and square the units. This s is still the surface area of the wings, which is meters squared. And then the c sub d is the coefficient of total drag, which, like its coefficient of lift counterpart, is a unitless value that combines all the other variables you would need to calculate drag into one convenient term. Now, you can use that one equation I did mention earlier to calculate drag, but again, only when the airplane is in equilibrium. Now, I would like to point out that drag only has to be less than thrust minus the weight of the airplane times the sine of theta if you want the airplane to work. Technically, drag could be greater than this, but then the airplane couldn't take off because there's too much friction. Similarly, lift could be less than the weight of the airplane times the cosine of theta It's just then the airplane still couldn't take off because it'd be too heavy. Now, there is actually one more equation for drag, and it involves the coefficient of total drag. We can actually split that apart into components. We can say that if we add the profile drag and the induced drag, we will get the coefficient of total drag. Now, we do still need to calculate our coefficient of profile drag experimentally. That's still how we'll get that. However, our coefficient of induced drag can be calculated from other terms. So there's an equation for that as well. And it states that C sub di is equal to C sub L squared, our coefficient of lift, times 1 over pi times AR times E sub O. Now, this denominator does require a little bit of discussion. Now, pi is the mathematical constant which you should all be familiar with. This AR is the aspect ratio of the airplane, and it is equal to b squared over s. Now, b is the wingspan, which is measured in meters. And because the variable is squared, I'll square the unit. And s is still the surface area of the wing, which is still in meters squared. Now, you'll notice that these cancel, so the aspect ratio is actually unitless. In fact, this entire equation involves unitless variables. Now, this E sub O is the Oswald efficiency factor, not to be confused with the mathematical constant. This subscript O is rather important. Now, because the AR, the aspect ratio, takes into account 2 dimensions, but wings are actually in 3rd dimension, we need this E sub O to account for that 3rd dimension. This essentially corrects so we can, have a more realistic equation for wings. So, and sometimes this 1 over pi times aspect ratio times E sub O is actually combined into k. So sometimes that's just written as k to shorten it. So we can kind of condense this equation. So we can say that the coefficient of total drag is equal to the coefficient of profile drag plus c plus the coefficient of lift squared times k. But that is lift and drag. I hope you enjoyed it, hope you learned something, and see ya.